Hello and welcome to the project demonstration for Fiona O'Connor's third year project in contribution to his computer science bachelor's degree from the University of Lincoln. The title is Exploring SkipConvGAN, an adversarial evolution of SkipConvNet for blind dereverberation. The objectives of the project were twofold. First, the intent was to explore SkipConvNet's ability for blind dereverb of speech specifically, using the Reverb Challenge database. Kopthali et al. Explored its general ability for dereverberation, but didn't discuss in their report or the GitHub repository whether it was particularly efficient at removing reverb from rooms that it hadn't seen before. So that was something that I wanted to have a look at. And also then to move on to exploring adversarial training with the architecture to introduce SkipConvGAN, which would hopefully bring with it lots of the benefits that GANs have in other areas of this kind of pixel-to-pixel translation, which is the domain we ended up in for the speech when we converted everything through to being spectrograms. So yeah, we were hoping that a little bit of intuition for recognizing the mapping from the reverberated signal to the clean target audio would be learned within the GAN training. The main architecture being used in the translation from the input to output signal is performed by a UNet style architecture, which has this encoder section which downscales but ups the complexity of the number of channels, and then this decoder section which upscales each of the size of each of the images within the channel, but does decrease the number of channels back to being one, or if you're doing RGB then it would obviously be three rather than just the one channel. At the end of each of these encoder steps, a output from that layer is saved, which then, as the symmetrical layers are moved up through, that is concatenated onto the input. So this would be concatenated onto there, this would be concatenated onto there, and that works as so. This gave a really good aptitude for kind of making assumptions about reduced sized images. So all of that information is condensed into these very small images. While they might not look like much, the UNet can then decide its course of action, kind of moving on from these smaller layers without losing the fidelity, because it is of the higher res images, because they are appended, concatenated to the inputs of these layer decoder steps. Yeah. SkipConvNet was proposed by Kothapalli in 2020, I believe. Yeah, 2020, as an improvement on the UNet architecture specifically for dereverb. And this improvement was largely introduced to combat what is considered to be a bias on the outputs of the encoder layers. So these are obviously not the input to the layer, but the output to the layer, which is then concatenated to the later decoder layers. And this has come under some scrutiny in very recent time as having a bias upon it from that convolution, which does make sense. So Kothapalli introduced these skip convolutional layers, which was a conv layer with a ReLU and a batch norm, which would hopefully remove that bias and allow the input of the skip connections to be a little more transparent and useful and reflective of the input at that stage, potentially. This did show great improvement in his results compared to a standard UNet for this use case. It hasn't been explored greatly in other use cases other than reverb, so that could be interesting in the future. But as it had just been proposed, and there were some questions I wanted to ask of it in terms of blind dereverb and some exploration to be had in GAN, I adopted this architecture publishing for my third year project. SkipConvGAN was my proposal for an improvement on SkipConvNet using adversarial training. GAN training or adversarial training has proven useful in many applications where something isn't so easily mathematically identifiable, such as the impulse response of a room based on speech, and needs a little more, say, human-like intuition for recognizing the kind of pix-to-pix problems, or image-to-image translation rather. And this used a conditional discriminator of this convolutional architecture, taken from or inspired by here, which took both the input and the output of the generator network, or just the input and the target, depending on whether it was acting on true or false inputs. Then it would try and decide whether what had been given was a correct mapping from input to target or a false mapping from input to output of the generator. It would be rewarded for getting it correct, and it would be punished for getting it wrong, and that would be a binary cross entropy loss. And then the generator would have a L1 loss, and the binary cross entropy loss of the discriminator. The L1 would be factored by a scale lambda, which I believe was 50, to give the binary cross entropy of the discriminator a benefit. So if the generator's L1 was close, it was a case of minimizing the L1 loss of the generator and maximizing the binary cross entropy loss of the discriminator when it is fed the false output from the generator. So basically the generator would be rewarded for fooling the discriminator, and it would be rewarded for a closer L1 loss, and it would be punished for the inverse of that. The training loop was for these two networks was as follows. First, the discriminator was trained, so it would be fed the input and the target data. It would get a binary cross entropy loss of how it correctly identified truths, the true prediction here, and then it would do the same for the output of the generator and the input, and that would be its false predictions. Those would be taken in equal part, added together, divided by 2, and that would be the loss of the discriminator, and then that would backpropagate. Next, the generator was fed input, and the L1 loss between the output and the target was fed to the loss of the generator, or considered for the loss of the generator, and also the output then was fed with the input to the discriminator to get a false prediction, and that would hopefully be, the error on that would be maximized. So that would also be considered for the loss of the generator, and then all of that would be used as the loss to backpropagate and learn. Here we can see the results of the validation data testing. So the validation data was from the same data set as the training data, but it was kept separate both in impulse response used to do the convolution upon the audio and in the audio itself. So none of the impulse responses in the validation data had previously been trained upon by the network. So here we can see that the SkipConvNet original architecture performed better in minimizing the L1 loss, or that's mean square error loss actually in these final output measurements. But and it did preserve a little more of the shapes in those spectrograms. However, you can see more artifacts within the SkipConvNet outputs. So there's kind of these weird square blocky things that you can see have been generated, which is less the case in the SkipConvGAN.
For it was one of the loveliest places you could For it was one of the loveliest places you could For it was one of the loveliest places you could For it was one of the loveliest places you could
Here we can see the results from the test data. The test data was completely separate from the training and validation data. It was samples taken from War Games experiment, and this had 4 subjects wearing lavalier microphones, recording clean speech, and it also had a series of wall and ceiling and table mounted microphones also that would pick up a collection of their voices with some reverb, but there was also some extra additive noise, which went outside of the scope of the training data, so there was no addition of noise aside from reverb convolutions in the training data. So this was really a test for how SkipConvGAN was recognizing and isolating speech itself, almost irregardless of what kind of noise it was obstructing it, as well as removing reverb. Now, this neither SkipConvNet or SkipConvGAN trained with the training data which was used improved the mean square error compared to the target, from the input to the target. However, the SkipConvGAN did get an awful lot closer, made much more of an improvement than the SkipConvNet, which shows that when you start wandering outside of the scope of the training data, the intuition of the GAN really starts kicking in. And I think that's a really positive sign. A lot of the information is lost, some of the speech you can't quite hear, but it's a difficult data set for a quite secularly trained neural net to then be applied to.
Know the rules all that well.
I don't.
So the conclusions that I've drawn from this project show that there's really much promise for SkipConvGAN as an architecture, and versatility for that architecture to maybe have some aptitude for performing well in slight movements adjacent to the scope of the data that's been trained on, which should give hopefully good, spidey sense tingles for reduced dataset training on this kind of architecture. If there was more of a variety in the speech corpora used in training, then there might have been quite a vast improvement in its performance on many applications, really. Also adding some extra noise, so just kind of, dog barks, printers, stuff like that, a little bit of white noise maybe to some of the inputs to the network during training could make it much more robust for real world use, such as, cleaning reverb off of ASR applications, or, and convolutional networks like this are sometimes used in embedded systems, such as is being proposed for hearing aids to improve the intelligibility and the reduction of babble noise as well as reverb. So yeah, a little bit more exploration, a little bit more variety in the data set. I think this could be a very usable, provable to be a very usable architecture and a very usable network once trained. Um, and yeah, thank you very much. I appreciate it. I hope that it was an alright watch. Alright, thanks.